Hello everybody, and welcome back to another video on my channel. Today we will have a full guide of a lot of the things that just spin around. And we will be covering rotational kinematics, rotational dynamics, and static equilibrium. So stay tuned, that's going to be really cool. And yep, I think that's really about it. And let's move on to the first topic. There's going to be three main topics we're going to talk about today. The first will be angular displacement. Now, what is that? Well, angular displacement is how many degrees have I rotated? Because angular displacement, so let's say I'm moving around in a circle. Oh, that was a bad circle, let me redraw that. Now, if I'm moving around the circle, and this is our starting position, I can either move around, I'm going to move around the circle and cover a linear distance of s, or it's the same as covering an angular distance of theta. And just like regular displacement, if you wrap all the way around, the angular is 0. So that's essentially what angular displacement is. And it's related to regular displacement by s is equal to the radius of the circle times the angular displacement. And over here, I'm going to introduce my first animation. The second quantity that we are going to talk about is angular velocity. Well, what is angular velocity? Well, we know that linear velocity is equal to linear displacement, or delta x, over time. Or at least, this is the average velocity. Instantaneous velocity is different, requires calculus, but not the point for this video. What really happens, though, is that since you have that, linear velocity is equal to that, you would think that angular velocity, or we call it omega, is equal to displacement over time. And if you thought that, you would be absolutely correct. This is exactly what angular velocity is. And we can even relate it to linear velocity, because angular velocity is delta theta, or basically the regular displacement or linear displacement, divided by r, and then times delta t. And s divided by delta t is linear velocity. So this is equal to linear velocity by the radius of the circle, or v is equal to r omega. Now, I'm going to show my second animation, which illustrates this pretty clearly also. For our final thing, we are going to have angular acceleration. This follows pretty much the same pattern as the other one. Linear acceleration is delta v by delta t. And what's next, right after that, is you have, then this becomes delta omega by delta t, and angular acceleration, which we call alpha, is equal to regular acceleration over the radius. And those are all the things, except quickly one more thing before we move on to our final animation, which shows acceleration. All of these, angular displacement is in radians, angular velocity is in radians per second, and angular acceleration is in radians per second squared. And this shows the units for each of these quantities. So now let me show you my final animation displaying angular acceleration. the actual definition of torque, and torque is written like this, sort of like a lowercase t, but instead, not lowercase t, sign of like a mini uppercase T with like a hook almost, like a hook and then a line on top of it. This is the cross product of the force vector and the displacement vector. So this means that torque is also a vector. And by these units, by this thing, the units of this are Newton meter. Now you might be like, wait, isn't this a joule? But no, this is not a joule. This is specifically a Newton meter. So that's why when we talk about joules and energy versus this, they are two different things. Because if you remember, energy was the dot product versus the cross product. So those are two different things. Now, the magnitude of torque is equal to the magnitude of the force times the magnitude of the displacement vector times the sine of the angle between them. Now, basically what this means, that means if I push in the same direction as the object, like as the displacement, that means I'm just going to push it translationally, and that's just regular force with no torque involved. But besides that, the other thing is if I took directly perpendicular, I will get the maximum amount of torque. But if you notice, about work, since it's a dot product, that means I will have no work done. Since I'm not actually moving it, I'm just making it rotate around its center of mass. Speaking of center of mass, that is something we're going to talk about in a video in the near future. So, now that all of that is explained, let's draw a diagram to explain how this works so you understand it better. So, torque essentially acts like kind of like a lever. And for this, we're going to say we have a hinge over here. Now, let's draw a rod like this. So, and let's say the force, we apply the force over here. So, the distance from the application of the force to the hinge is the distance r. And let's say we apply the force like this. Now, if you notice, this angle with the horizontal in green is the theta in our equation. This maps to this, and this maps to this, and then of course you just have the force that you're applying to create the torque. Now, this is just a one-sided hinge. There are also other applications. Let's say we also can have like a seesaw, or what's called in physics also a first-class lever, and instead this is the center point. So if it was here, this wouldn't be the distance, and this wouldn't be the distance. Instead, what would be the distance? It would be between here and the center. And this would, if we had a weight on here, this weight would go straight down or perpendicular to, so the torque would just be the force applied on this, and many problems will ask you to balance this lever. So you'll have to balance the torques, not the force. But that's something more relating to static equilibrium. So I think that's really about it for introduction to torque. I'm going to keep these intro videos relatively short, so when I explain more things, I can actually show you problems where it's actually going to be used instead of just something very basic that you're probably not actually going to use. So, thank you so much for watching this video. See you in the next one, and bye-bye.